most of the time we actually use isoparametric, and say subparametric in case, in fact in isoparametric when you use higher degree polynomials, subparametric is in fact included in that, because what happens is when you interpolate the geometry, even let's say if you use biquadratic polynomial in xi and eta and interpolate both xy as well as the field variables, and if the element shapes are simple, maybe say simply maybe quadrilaterals, of course if it has curved edges then the quadratic terms also become important, but if the element sides are straight, then automatically the xy would be only finally after you do the calculation and express x and y in terms of xi and eta for given x1, y1, x2, y2, x3, y3, x4, y4 and so on. So you will find that that would be only linear in xi and eta, whereas interpolation of your variables would be quadratic. Of course again depends on finally how the problem, boundary conditions and domain and everything. So the in isoparametric, subparametric is kind of embedded, but when you want to do the super parametric, and most of the time you don't want to do that because geometries might be complicated, but then anyway you are breaking into a number of elements, and more importance is given to the field variables. Whereas because in super parametric formulation what you are doing is interpolating the geometry using higher degree polynomial and lower degree for the field variables, and which is often not the case. Because the geometry might be complicated, but it is not as complicated as the distribution of field variables itself might be there. So one really does not use these two, sub and super parametric, it's only isoparametric which is used, and in that subparametric is actually included in it. So depending on the shape of the element, automatically final expressions for x and y reduces accordingly. So even if it is initial assumption is quadratic, but final expression would be coming out as linear in xi and eta only.
For that F integral we have ds, right?
Yeah.
That ds will substitute directly the natural coordinate.
No, not the natural coordinate. So you have to express your length in terms of natural coordinate. No, so now you have x and y. So suppose if you are moving along a line, which is let us say a straight line or y equal to fx. So then you write ds as the square root of dx square plus dy square, and dy you can write it as you take the dy by dx and dx as common. So that is how you would, and then dx you would express in terms of d high and d eta. So if there are many intermediate nodes other than yeah, so the concept is same, of course. Again I am going to discuss about, there are two types of elements. One set is known as Lagrangian finite elements and others are referred to as serendipity. So there are for the Lagrangian it is always easier to write the shape functions, but for the serendipity is when we go more than 8 nodes, 9 nodes is a Lagrangian element, so you can easily write that, but when we go for the only the nodes and the boundaries of the element, for those writing shape function is actually a bit difficult, but then what you can do is assume a polynomial and then express all the constants in terms of the values of the variable at node points, and then from that you evaluate your shape function. So that can easily be done. But writing the shape functions from inspection like what we were doing, that is not easy for number of nodes more than say 9. I mean for serendipity class of particularly elements. So are there any other questions? So I think the design students are here now, we can start. So are there any other questions? See, so far what we have done is we were discussing about, there were a couple of questions. So I think we were discussing about isoparametric formulation. So one question was, how do we decide when to use subparametric, when to use superparametric or isoparametric? So answer to that question is, most of the time we actually use isoparametric, and you hardly find the use of superparametric finite element formulation. But in the isoparametric, actually your subparametric is in fact included. So for that, what you can do is, if you want to look as an example, if you want to see, what you can do is, let us say I'll do a simple case. So let us say that we have a element in the physical coordinate space which is actually a rectangle, but it's 8 noded. So 8 noded, these are the corner nodes and mid side nodes. So if you want to just look at that, what kind of finally we get the and let us say, for the timing, to simplify our calculations, that our coordinate system is having origin right here at the first node. So this is local node 1, 2, 3, 4. This is typically the numbering scheme, although you can actually use any numbering scheme for the local element numbers. So that is node numbers 1, 2, 3, 4, 5, 6, and let us say that my global coordinate axes are having origin at the first node of the element. This is just for the simplification. So then the xy coordinates here are 0, 0. Let us say this is a by 2 comma 0, and this would be a comma 0. This would be a comma b by 2, and this is, let us say, a comma b, and so on. So you can write the coordinates of all other nodes. Now if in this is the element in the physical coordinate space, and of course you are mapping this to the natural coordinate space with xi and eta, and this is your xi and this is your eta, and same nodes, there are corresponding nodes here, 1, 2, 3, 4, this is the corner, and then 5, 6, 7 and 8. Now if you are writing, let us say, x, how will you write x? X is going to be n1 x1 plus n2 x2 plus n3 and so on. So as you see here, this is going to be ni xi, where xi are the nodal x coordinates and ni's are the shape function, and I is going from 1 to 8. Okay, this is, I am just trying to show you that you will find, although this is with 8 nodes, both xy and xi variable of interest, field variable, are interpolated actually using quadratic polynomials. But when we look at the final expression for x, it would be only linear in xi and eta. X will linear in xi, in this case y will turn out to be linear in eta. So that is what I wanted to show you. So now if you look at the coordinates, n1 x coordinate is 0, so that contribution is 0, and then this is going to be n2 into a, so plus you will have n2 into a, and then if you look at so n3 into a, so I actually can put n2 plus n3 together, because x2 and x3 coordinates are same. So this is n2 plus n3 into a. I am writing n1 x1 plus n2 x2 plus n3 x3. See, this is x1 which is 0, x2 is a, x3 is also a, and then x4 is 0. Then you come to x5 which is a by 2, so you will get a by 2 into n5 plus this 6, so plus you will have here x coordinate is a, so a into n6, and for n7 again you have the x coordinate as a by 2, so plus a by 2 into n7, and for a8 x8 is 0, so these are the terms you have. And now if you look at the expressions, what are the expressions for n2 and n3 I had given? Can you someone tell me that? So we have minus 1 by 4, so let me write that a also here, so minus a by 4 outside, and then this is n2 is 1 plus xi, for 1 it was 1 minus xi, so n2 must be having 1 plus xi, no? 1 plus xi, 1 minus eta, and then 1 minus xi plus eta, is that right? And then n3 1 plus xi, 1 plus eta, 1 minus xi minus eta. So this is the no, the first set, that is basically this one. And what we can also do is combine this n5 and n7 because they have this common a by 2. So what you can write is, and then in n5 and n7 you will have actually 1 by 2, so I can write as 1 by 4. And then what is the a by 4? What is the expression for n5? We want to write here n5 plus n7. So n5 is 1 minus xi square into 1 minus eta, and n7 expression, n7 is again basically 1 minus xi square and 1 plus eta, right? 1 minus xi square into 1 plus eta, and plus the last term, which is a into n6, so that would be a by 2. And what is n6? n6 is 1 minus eta square, and then 1 plus xi, so 1 minus eta square into 1 plus xi. So this is what you get finally. And now if you simplify this, just simplify and tell me what you get out of this. No, that this is a into n6, n6 you will have 1 by 2, so that is 2, that is what I have written. Here also, because you are talking about this, no? So in this also n5 and 7 both 1 by 2 is there, so a by 2 into divided by 2, that is what I have written, a by 4 here, no? See, this is a by 2 into n5 plus n7, and in both n5 and 7 you have 1 by 2 into that expression, so that's how I written it as 1 by 4. So if you simplify and look at what you get, so maybe what we can do is for the simplification of this, you can take 1 plus xi common, then you have to multiply and cancel some of the terms. You can actually do quickly that. So take 1 plus xi common. I think 1 plus xi is the only one which is common. So you get 1 plus xi common here, and then if you simplify you get 1 minus eta this and these terms. So let me expand that. So 1 minus xi plus eta minus eta plus xi eta minus eta square, that is what we get from the first one, and then plus 1 minus xi minus eta. I mean a bit algebra here, and then plus eta minus xi eta minus eta square. So that's from the first one. You will find that some of these things would cancel out. So this term will cancel out with this eta gets cancelled, and this is anything else. So this gets cancelled with this, and then what you will be left with is anything else. This is minus xi plus 1 minus eta square. So that's all what you get from this. And then from the second one we can take 1 minus xi square common, so plus you have 1 by 4, 1 minus xi square, and then 1 minus eta plus 1 plus eta, so that is simply 2. And of course this is of course as it is a by 2 into 1 minus eta square into 1 plus xi. Now if you further simplify this, so what is the final expression? I hope we have not made any mistake here. So you have to open up all of these terms. So let me take a by 4 common everywhere and then write all the terms. So here you will have is of course that minus sign also. So with minus 1 plus xi, and this is minus plus 2 eta square, and okay, that's so 1 plus 1 2, so I can take that 2 here. This is 2 xi, so this is taken care, this is taken care, minus xi is taken care, eta is taken care, so that is my plus 2 eta square. Okay, and then you multiply that with minus xi, so you will get minus again, so minus 2 xi, and then plus 2 xi square n plus 2 xi eta square. Pardon? So what is the final expression after the simplification? So the other terms, now when you combine all of these, so what I was trying to tell you is that this will be 2 minus 2 xi square. Let me do it quickly. And here also we will have, let's say, 2 plus 2 xi minus 2 eta square minus 2 xi. I think this is what you will get. So now if you see some of these terms, so this gets cancelled with this, and this term gets cancelled with this, 2 eta square, this gets cancelled with this, and this 2 and this 2 get cancelled, and this 2 xi gets cancelled. So what you have is finally this has age high by 2 as your x. So what it implies? That although where is 1? Yeah, this 2 is left out, right? Yeah, okay. So this is 1 plus xi, right? Yeah, thanks for this correction. So what you finally see, although as an approximation, we assume that x is biquadratic in xi and eta. So the starting point is this, that x is equal to ni xi, and actually that came from obviously b0 plus b1 xi and so on up to xi square eta square terms, and finally we wrote all of that in terms of shape function. So we got this. So our initial assumption is that, but since the element shape in the physical coordinate space is a rectangle, so here you will find that automatically you get x as a linear in xi, and although your variable depending on say temperature or displacements, depending on their variation, they will come out as quadratic within the element. Of course, even if the solution is also linear, then it might turn out to be linear. So you would see that finally what we have is x is linear in xi. So same way, if you look at y equal to ni yi, and I going from 1 to 8 for the 8 noded element. And why I took 8 noded? Because here you have quadratic. So I wanted to show that finally the x reduces only to a linear in xi, and y reduces, so you will find similarly this would be b by 2 into 1 plus eta. You can do the same exercise what we did for x. You will find that this y will turn out to be this. So you see here x is linear in xi and y is linear in eta. So you can say now that x and y are interpolated as linear functions of xi and eta, whereas field variables either temperature or u and v are interpolated using still the quadratic polynomial. So you see that sub-parametric formulation is actually embedded in this. So this you can check. I mean, it comes in the same form. That, and if you check back again, the actual coordinates. So relationship between if I want one-to-one correspondence here and here. So for this point, xi and eta are -1, so you will find that x will turn out to be 0, y will also turn out to be 0. And if you put any other coordinates of the points, you will get that corresponding coordinates of the physical space. And now if you look at your particularly Jacobian matrix, so J here, the Jacobian matrix, if you remember what we had said was, this is del x by del xi and del y by del xi and del x by del eta and del y by del eta. And now in this case you see that this Jacobian matrix del x by del xi is going to be a by 2, but del y by del xi is 0, and then this is del x by del eta is 0, and del y by del eta would be b by 2. So this now you automatically find that this cross derivatives here are 0 for an element which is rectangle in the physical coordinate space. And then if you want to find out the determinant of the Jacobian matrix, so as you see determinant of J is simply going to be AB by 4. So essentially it is 1/4 the area of element in the physical coordinate space. So because now if you want to calculate the total area of the element, so total area of the element would be integration from -1 to +1, -1 to +1, determinant J d xi d eta. So this is how you will evaluate. and determinant j we have seen it is AB by 4, then it simply reduces to integration -1 to +1, -1 to +1, and no d high d eta. And when you do this integration AB by 4, d high integration is just high, and when you put the limits 1 minus -1, so you will have 2 into 2 when you evaluate this integral. So finally you get AB by simply AB, which is the area of actually the element in the physical coordinate space. So automatically this gives you the total area, and you will find of course in this case that the derivatives with respect to x and high are directly related. So same way when you are looking at now, if you look at J inverse for this case, so J inverse is going to be is simply this whole thing divided by the determinant, so 4 upon AB, and if you just interchange these, so then what you will actually get is this as 2 by A 0 0 and 2 by B, right. So this is your J inverse. So you will find J inverse gives us relationship between del by del x. You will find that del by del x is going to be simply 2 by A into del by del high. Now no eta term because this term is 0, and similarly derivative with respect to y is simply 2 by B into del by del eta. No high term in this operator relationship. So they are just related 1 to 1. This is B here. And so this is about how the subparametric formulation is embedded actually in isoparametric formulation. So it simply is governed by the shape of element in the physical coordinate space. Now the same thing what you can do is you can, as an exercise you can try, if the element in the physical coordinate space is, let's say, a general quadrilateral but with the straight edges. So still a 8 noded element. Here you have again the 8 nodes, so the nodes are 1 2 3 4 5 6 7 and 8, and you can still take the coordinates as, let us say, this as x and this as y, and write the coordinates. So here it would be 0 0, and accordingly you will have to of course assign the coordinates to all of these nodes for a general quadrilateral, and then this you are mapping to a square element in the natural coordinate space. In this case you will find, if you do the same steps, you appropriately take the coordinates, and if you follow the same steps, you will find in this case that high and eta, x and y would be linear in high and eta. So x will have both high and eta term, so but no quadratic terms. Like here what we had is x is only having high, y is having only eta, and if you take x and y, for this particular case you will find x would be having high as well as eta term in it, but no quadratic terms, and similarly y will have high and eta terms in it, but no quadratic terms in it. So again we start with a quadratic approximation of x and y, but depending on the shape of the element in the physical coordinate space, it automatically turns out only linear in high and eta. So this exercise you can do, take some appropriately the coordinates, so that it's actually a general quadrilateral, and maybe simple case could be that these two edges are parallel to x and y, only these are inclined, or only one is inclined, so that your calculation can be simpler. So choose the coordinates accordingly, you would see that finally it reduces to only linear in high and eta. So that is why I said subparametric formulation is embedded in the isoparametric formulation. Okay, so then let us continue. So for us, the question you asked, you had asked some question at the beginning. Yeah, so the another question was, I think that when we take some examples we will talk about that. So the internal load vector I had left in terms of ds, that ds is the element length, element boundary differential length in the physical coordinate space. But since there is the quantities which you are integrating are functions of xi and eta, so ds also has to be expressed in terms of xi and eta appropriately. So ds you can write as say square root of dx square plus dy square, and then x and y are written in terms of xi and eta, so things like that we'll have to do. So let us now continue with what we were doing. So we said that finally whatever the problem is, the element level governing equations are of the same form. So we had said that element level governing equations are of this form, that we said that no Ke for, let's say, for the heat conduction problem we can write this. So I am going to talk about numerical integration, that is what I mentioned in the last class. So we have some because of the distributed source terms are forces given, you have external load vector, and then because of the boundary forces from the surrounding elements, you have this internal force vector or the source term. And we had said that, say for example, for heat conduction problem this was -1 to +1, -1 to +1, and then we had K into B transpose into B and into determinant of J into D high into D eta, and similar expressions for the other quantities. So now one important thing is the integration of these quantities. So we need to evaluate these integrals, and quite often because the matrices B and all are going to be of larger size, and if the element is not actually a rectangle in the physical coordinate space, then this J is also going to be function of xi and eta. Actually it can have 1 upon xi, 1 upon eta kind of terms. So then the integration explicitly would be actually difficult. That means explicit means you want to multiply everything and then you integrate each term from -1 to +1 with respect to xi and eta. So that's usually difficult. So what we do, we evaluate these integrals using numerical integration. So theoretically you can use all the numerical integration techniques you would have learned, like trapezoidal rule, Simpson 1/3, Simpson 3/8 rule, and so on. But if you use simpler integration rules, then the number of calculations might be larger. So what is found in commonly used numerical integration technique here is Gauss quadrature numerical integration. So with minimum number of computations you are able to evaluate these integrals accurately. So that is why we use that. So numerical integration, that is what we are going to talk, and actually I am going to just concentrate on this Gauss quadrature numerical integration. So I had actually briefly introduced this when I was talking about reduced integration for eliminating shear locking in case of Timosenko beam element. Ultimately, if you see, when we multiply, essentially what we want to do is we will have to integrate each and every term of this resulting matrix after the multiplication. So whatever we use for is the integration of a scalar function, same thing is applicable for the matrices as well. So first let us consider that we want to do an integration. Obviously all these integrations are from -1 to +1. So we have a scalar function which is a function of xi and d xi. Let us say we want to evaluate this integral. So numerical integration means maybe if you recall your the basic calculus when you would have learned the differentiation and integration. So that time you were taught that the integration is the limiting case of actually summation. So again we are going back. So rather than this continuous integration, we want to do it as a discrete one. So we want to represent it as a summation. So we write it as I, say I equal to 1 to n, and we evaluate this function at these points. So let us say xi I and multiply by some weight factor wi and sum it over all the n points. We get we approximate this integral by this summation. Rather than doing the explicit integration, now you are doing this summation. And if you use f xi I as fi, you can do that. So you can also say that I equal to 1 to n fi into wi. For fi, you are saying that the value of f at xi equal to xi I. So this is what is this numerical integration. Now in this numerical integration, see xi i's are known as actually Gauss points in this case, or more general terminology is sampling points. So this is here. But in Gauss quadrature numerical integration we popularly call these as Gauss points, and wi's are known as weight factors. So once we know that for a given problem, if Gauss points and weight factors are known, this evaluation is actually straightforward. I'll maybe a brief description about what we actually mean by this. So when we are trying to do in Gauss quadrature numerical integration, what we are trying to do, one thing is that if we have this f xi, we are actually approximating it as a polynomial. So if it is already a polynomial, then there is actually no approximation. But if it is other than function which is other than a polynomial in say xi, then it's an approximation. So let us say that it is polynomial, it is approximated as polynomial of, let us say, order maybe p. So then let me write it as something like, say, a0 plus a1 xi. This is nothing to do with the interpolation we did for the field variables as well as xy in the isoparametric formulation. We are just saying that we have some function f of xi. It could be trigonometric function, it could be a polynomial itself, it could be 1 upon xi, 1 upon eta kind of function. So it can be any of that. What we are saying that we are approximating it as a polynomial. So a0 plus a1 xi plus a2 xi square, and plus, let's say, we have terms up to xi power p. So what we are saying that whatever function we have got here, which is to be integrated, we are approximating it as a polynomial. So when you say Gauss quadrature numerical integration, implicitly actually there is an approximation of the function as a polynomial. And then now if it is a polynomial, of course we can also do exactly this integration. So if I want to evaluate the integral I, which is integration minus 1 to plus 1 f xi d xi. So now if I approximate f xi by this, so I can write this integral. This would actually be an approximation. If it is a polynomial and having the highest power of xi as p, then it would be an exact evaluation of the integral. Otherwise it would be an approximate evaluation of this integral. So I can say that this I is minus 1 to plus 1 f xi d xi. Since it is a polynomial, I can integrate it exactly. So a0 integration minus 1 to plus 1 will give you 2a naught. That is xi, and the limits are upper limit 1 and lower limit minus 1, so it would be 2. And the integration of this term would be xi square by 2. When you put the limits plus 1 and minus 1, it will actually 0. And when you take similarly this, so this would be 2a2 by 3 similarly, because xi square integral will be xi cube by 3. When you put the limits, you will get essentially 2, and so on. So like that you will have these terms, and plus the last term is now when you do the integration, so it is going to be ap upon p plus 1 and xi to the power p plus 1. When you put the upper limit, so it is 1 to the power p plus 1, which would be 1. So you will get 1 here, minus lower limit is minus 1 to the power p plus 1. And this value depends on what is the value of p, so that is why we are writing it as it is. So this will be the integration of the approximate function f xi, which is approximated as a polynomial like this. And if it was polynomial indeed with highest power of xi less than or equal to p, then this will be an exact integration of this function f xi. Now this is the after approximation, the explicit integration of f xi. The other way, through the Gauss quadrature numerical integration, we are writing this as, so say if we are using n number of points, so then we are writing this as, so f1 into w1, that is this summation what I just said here, fi wi using n number of points. So this is f1 w1 plus f2 w2 and so on, plus we will have fn wn. That is n number of points are used here through the numerical integration. So this is how the formula for the total evaluation of this integral I would look like. And now if you want to, again we want to relate actually these two, this and this. So here f1, f2 or f3 are nothing but the values of f at xi1, xi2, xi3. So I can replace f1 by putting xi equal to xi1 in this expression. f2 I can replace by putting here xi equal to xi2. So see, this further can be written as f1 means a0 plus you have got a1 xi1 plus say a2 xi1 square, and finally ap xi1 to the power p into w1 plus this is the value of f1 evaluated from here, and then similarly plus f2 is nothing but then a0 plus a1 xi2 plus a2 xi2 square plus ap xi2 to the power p into w2 and so on. No, so similarly, no, you can write all of these terms, and finally you can write no, for the nth term a0 plus a1 xi n plus a2 xi n square and so on plus ap xi n to the power p into wn. So what we have done, whatever the summation form for I we have, in that we are just substituting the polynomial approximation of f xi, that is this. Here putting f1 means evaluate this function by putting xi equal to xi1, f2 means evaluating this expression by putting xi equal to xi2 and so on. And now what we are saying, that if f xi was indeed a polynomial with highest power of xi less than or equal to p, then no, these two, this integration and this integration must be same. And now for these integrations to be same, that means the coefficient of a naught from both these expressions must be same, irrespective of the coefficients a0, a1, a2, a3 representing the polynomial. The two expressions, that is expression for I given by this and expression for I given by this, must be same. So if you now equate from, let me call this as equation 1 and let us finally call this as equation 2. So by equating the coefficients of from equations 1 and 2, by equating the coefficients of various a0, a1, a2, a3, we generate actually a number of equations. So from these, one is if I equate the coefficient of a0 from both, so you see that from this a0 coefficient is 2, and from the summation side the coefficient of a0 is w1 here, w2 here and wn here. So you will find that this is going to be w1 plus w2 finally wn is equal to, so this is because this is entire summation, this term, so many terms than this. So a0 is here, a0 into w1 plus a0 into w2 plus a0 into wn. So you will have w1, w2 up to wn as the coefficient of a0 in this equation 2, and this must be equal to the coefficient of a0 here, which is actually 2. So this is equal to 2. This is one equation. Then now if I take the coefficient of now a1, so again the same thing, here the coefficient of a1 is xi1 into w1, here xi2 into w2 and so on. So we will have xi1 into w1 plus xi2 into w2 and so on. So you will finally get plus xi(n) into wn is equal to, this is the coefficient of a1, and in the exact integration that is 0. So this must be equal to 0. Then similarly, if you look at the next one, you will have xi1 square, that is coefficient of now a2 if you look at. So again here you will find that here coefficient of a2 is xi1 square into w1, xi2 square into w2 and so on. So xi1 square into w1 plus xi2 square into w2 and so on plus xi(n) square into wn, and this is equal to, the exact integration has the coefficient there 2 by 3. So this is 2 by 3 and like that. So you can write these equations. So final one you will get highest power when you are equating the coefficient of p. So that is going to be xi1 to the power p. So xi1 to the power p into w1 plus xi2 to the power p into w2 plus xi(n) to the power p wn is equal to, the coefficient that side we have is 1 upon p plus 1 and into 1 minus 1 to the power p plus 1. So these are the equations you get by equating the exact integration of polynomial approximation of f xi and the numerical integration through the summation of weighted sum of the function values at n number of points. You get these equations, and why we write these equations is kind of looking at how do we find out the these Gauss points and the weight factors. So if you look at here, if we want to look at the number of unknowns in terms of your Gauss points and weight factors are, if it's a n point integration, then there are 2n unknowns, because to n Gauss points, Gauss point locations and n weight factors. So if you look at here, the unknowns are equal to 2n, those are nothing but your gas points and weight factors. Number of equations are, how many equations do we have? Equations are p plus 1. No, this is like 1 and then you start with 0, like power is 0, then 1, 2, 3 up to p. So these are actually p plus 1 equations. And if we choose n and p appropriately, or let's say for a given p, we choose n appropriately, we can always find out n such a way that 2n is equal to p plus 1. So if we choose n such that 2n is equal to p plus 1, then what we will be able to do is we would be able to get the exact integration of the polynomial approximation of the function. And if it is indeed a polynomial, then obviously it would be the exact integration of the original function. So that is where here you decide. So you can say that the number of gas points n would be p plus 1 by 2. So means if you are approximating a function and the highest degree highest power of xi in that function is p, then you add 1 and divide it by 2, and obviously if p is actually, let us say, odd, then there is no problem, but if p is even, then this would come out as a fraction. So then you approximate it to a next integer. So this is always approximated to a next integer, and if you choose that many number of gas points, then you actually get the exact integration of approximated function f xi. Okay, so this is how you I had mentioned when I did discuss about the numerical integration, that number of points if for exact integrations are highest power plus 1 divided by 2 approximated to next integer. So this actually comes from this analysis. Then these equations can also be used to find out the weight factors and the gas points. So now if I choose, let n equal to 1, that means we just want to use 1 point integration. So if it is n equal to 1, then you have only one weight factor and one gas point. So all others are not there. So this equation is w1 equal to 2, and then xi1 you will find it will be equal to 0. So for 1 point integration rule, you will find that xi1 would be actually 0 and w1 will be actually equal to 2. And for n equal to 1, if you are using n equal to 1, then you would be able to integrate. What is the kind of polynomial you can integrate exactly using 1 point integration rule? You can only exactly integrate a linear polynomial, because when you put n equal to 1 here, so this is 2 minus this side 1, so p will be equal to 1. So it's a function which is linear in xi. Now if you choose n equal to 2, then you will have two gas points and two weight factors. So there will be total number of unknowns 4, w1, w2, xi1 and xi2. So you choose out of these 4 equations, first equation w1 plus w2 equal to 2, then xi1 w1 plus xi2 w2 equal to 0, xi1 square w1 plus xi2 square w2 is 2 by 3. The next equation would be xi1 cube plus xi1 cube into w1 plus xi2 cube into w2 equal to 0 again, and you solve those 4 equations. When you solve these 4 equations, you find that xi1 comes out as a plus 1 upon or minus 1 upon root 3, and xi2 will come out as plus 1 upon root 3, and the corresponding weight factors are w1 would be 1 and w2 will also be equal to 1. That is of course the solution is actually not straightforward, because you see the equations are nonlinear. So they are nonlinear simultaneous equations involving xi1, xi2 and w1 and w2. So what one can solve, see the other way of looking at these, the interpretation of gas points is actually they are essentially roots of Legendre polynomial of order 2. So if you take Legendre polynomial of order 2, find out its roots, that is what you will get those roots as plus 1 upon root 3 and minus 1 upon root 3. So similarly, if you choose n equal to 3, then you will have to actually take 6 equations. So w1 plus w2 plus w3 equal to 2, and then xi1 w1 plus xi2 w2 plus xi3 w3 equal to 0, and so on. So you choose those 6 equations and solve for xi1, xi2, xi3. So what you find is, let us say xi1 comes out as 0, and maybe xi2 comes out as let's say put 3 by 5. So minus, one is minus, another is xi 3 is 3y5. So actually FEM books you find that these are actually tabulated, these weight, gas points and weight factors. So W1 comes out as 8 by 9, and corresponding to these W2 is 5 by 9, and W3 is also 5 by 9. So this is for 3-point integration rule. These are the, you can like that. So in fact what I do is, because when I use some more complicated functions, so I have a subroutine. So even if I want 200 gas points and corresponding weight factors, that subroutine generates those gas points 200, 400, just 1 or 2 or 5. So one can actually write that kind of a subroutine to generate the gas points and the corresponding weight factors. So once you have this, so now if you look at similarly n equal to 3, so you would be able to, now if you want to look at what would be the kind of polynomial you can integrate. So see 3 into 2 here, 6 minus 1. So basically you can exactly integrate polynomial which is quantic, that is involving highest power of xi as 5. So this is how you get actually these gas points and the corresponding weight factors. Now the integration then is simply the summation. So for example, if you just want to look at, I don't know whether when I was discussing about shear locking, so I took some example or not. So let us say now simply I want to do the integration of a function from -1 to +1, and let us say that function is simply 2 plus 3 xi. 2 plus 3 xi. Let us say we want to do this integration using numerical technique. So we see that highest power of xi is actually 1. So we need how many gas points? 1 plus 1 by 2. So actually 1 gas point is enough for this. So that is what we said. 1 gas point means simply we evaluate this function at xi equal to 0 and multiplied by 2. So at xi equal to 0, this function is 2 and into 2. So actually the value would be 4. Exact integration also you can see. This is xi square by 2, so that contribution would be 0. So this is 2 into xi, and when you put the limit, so you see the numerical integration and exact integration is giving you the same number, which is 4. Of course, when you are doing this thing in the computer, there are some truncation errors because the numbers are truncated because of use of finite number of bits for representing the number. So that will be there. Otherwise, you will get otherwise exact integration. So now let us say another polynomial -1 to +1. Let us say 2 plus 3 xi, and maybe let us 3 xi. So this is 3 xi. Let us say 4 xi square I put, and d xi. And now if you want to integrate this, let us say using 1-point integration, then what you get? So if you use 1-point integration, this is your I, and value of I for n equal to 1, you will get I is equal to, you will get still the same thing, because a 1-point integration rule means only 1 gas point xi equal to 0, so it is going to be simply 2 into 2, which is 4. If you use n is equal to 2, so let us see what we get. So for n is equal to 2, I would be this function evaluated at, for 2-point integration rule, the gas points are -1 upon root 3 and +1 upon root 3. So the function evaluated at -1 upon root 3, so this will be 2 and plus 3 divided by, actually, so let me put a minus there. So this is by root 3, that's the function value first at xi equal to -1 upon root 3, plus this will become 4 by 3 into weight factor is 1, then the function evaluated at xi equal to +1 upon root 3, that will give you function value as 2 plus 3 by root 3, and of course this part would remain same, which is 4 by 3 into 1. This is through 2 points, and now if you work out, so you will find that this term and this term get actually cancel out, this plus this is 4 and plus this is 8 by 3. So this is what you get, 12 plus 20, this is actually 20 by 3. So now what is the observation here, and what is the exact value of the integration? It is actually 20 by 3. So you find that here we get only 4, and this is something like 6.667. So if we use less number of gas points, the integral actually is under evaluated. So here compared to exact integral value, you are getting the lower value. So that is what is we use for eliminating the shear locking reduced integration. So we evaluate it on the lower side compared to its exact value. And now let us say same thing, I want you to appreciate that. Let us say if you use n equal to 3, and then what happens. So please do that and tell me what do you get if you use n equal to 3. N equal to 3 means now you are going to use 3 gas points, xi 1 equal to 0, xi 2 this minus square root 3 by 5 and plus square root 3 by 5. So if you do that, so at 0 of course you get 2, and into the corresponding weight factor is 8 by 9, and then plus no, the whole function is evaluated at so this will be 2 plus 3 no, minus again, because one gas point is negative. So this is 3 into root 3 by 5 and plus 4 into 3 by 5, that is, and into this value is 5 by 9, the weight factor, plus here you will get 2 plus 3 into root 3 by 5 and plus again you get 4 into 3 by 5 into 5 by 9. So now what do you get? So if you look at, now you have to simplify this. So first term is 16 by 9, and this of course will get cancelled out with this, and this is 10 by 9 plus 10 by 9, which is 20 by 9. So you get one term as 20 by 9, and the last term would be no, so what you get that as 1224 into 5 by no, why, yeah, so this is 4 3 is 12 into 5, and they are combining this, so divided by 5 into 9. So then finally what do you get? This, yes, this comes as, what is the value? This is coming as 60 by, so 20 plus 24, so this is, yeah, 44 and 50, yeah, 60 by 9. Did I make any mistake anywhere? So this is 20 by, yes, 3 is right. Okay. So what do you observe? What is the observation from these two? So if you use number of gas points more than minimum number, then always you will evaluate the get the same value. So it is not that if we use more points, maybe the integral would be over no, evaluated. So you will always, if you use a number of gas points more than a certain minimum number, you will always get the same integration value if the function which you are integrating is a polynomial. That's the only condition. So this is how we use the numerical integration for doing the evaluating the integrations. Now let's say coming back to the problem what we were talking about. So if I look at this KE, now this for 1D cases, KE we have got as minus 1 to plus 1, minus 1 to plus 1, then we have say K into B transpose into B into then determinant of J into D high into D eta. And this we want now, this is a double integration, so we will replace this by a double summation. So the double summation would be, say I is equal to 1 to n, and in the other direction J is equal to 1 to n. Usually we in the double summation we keep the same order of integration. So either in both directions, 1 point integration or 2 point or 3 point, we do not, although theoretically we can have a different number of points along the xi direction and different number of points along the eta direction, but usually we keep these same. So this is also n, and then what you are saying that this whole thing K into B transpose into B into determinant J, this you are evaluating at xi I eta j and then multiplying by the weight factors wi wj. So if it was 1D integral, you are simply doing fi into wi. Now this is a two-dimensional integration, so this function is evaluated at xi I eta j. Xi I means the essentially gas point along the xi direction, eta j is the gas point along j direction, and then the weight factor corresponding to xi direction, weight factor corresponding to j direction. So this two-dimensional 2D double integral is actually replaced by a double summation like this when you want to do the numerical integration. So now let us say for the time being that n we are choosing as 2. So this integration is we are actually doing in the natural coordinate space. So this is my xi here, and this is your eta, and we are just doing, let's say n equal to 2. Of course if you are using only 1 point, so then this is only one evaluation, that whole of this function evaluated at xi equal to 0, eta equal to 0, multiply by 2 into 2, 4, you get that whatever value you get. Now, but if you are using 2 points, so what it means is that this summation I will go from 1 to 2, and for each I, j will go from 1 to 2. So what it actually means is that I know I will have a one point here, say xi 1 eta 1, then I will have another point here xi 2 eta 1, then I will have third point which is xi 1 eta 2, and then xi 2 eta 2. So we will have actually 4 points in all when we are evaluating this integral, because I is going from 1 to 2, for each I, j is going from 1 to 2. So ultimately we will get 4 terms. You understand, no, that when you expand this double summation, I think, no, if you don't follow, so it's like this, that when I am doing a double summation, I equal to 1 to 2, j equal to, I think there is a class here or so. So j equal to 2, and let us say that, no, we have a function f which is function of xi I, eta j, and wi, wj. This is what we have. Essentially what I wrote here is like that. This is for a scalar thing. So when you expand this, you take I equal to 1. So f of, you will have xi 1, and then the eta takes values 1 and 2. So xi 1 comma eta 1, then w1 into w1, and then for same I equal to 1, j also takes value 2. So f evaluated at xi 1, eta 2, w1, w2, and then now I equal to 2. So f of, you will have xi 2, and then j takes values again 1 and 2. So this is eta 1, w2, w1, and plus you will have f evaluated finally at xi 2, eta 2 into w2 into w2. So this is like no simple expression if you look at like this. So here what I am saying that no, this point is, let us say xi 1 and eta 1, this point is xi 2 eta 1, this point if you look at, it's actually xi 1 eta 2, xi 1 eta 2, and this point is your xi 2 eta 2. So if you are using n as equal to 2, then actually what you are doing is, this function is you are evaluating at these 4 points 1, 2, 3, 4, and then multiplying by the corresponding weight factors, and then summing up all of them together, you get the final integration value. So these points here are referred to as Gauss points. Now this is for 2 point integration, this point is actually minus 1 upon root 3, minus 1 upon root 3, this point is plus 1 upon root 3, and eta is minus 1 upon root 3, and so on. So these are your Gauss points. And now, but the question arises then, how do we actually choose this n? Now in this case, see, when I have a simple function like I was talking about here, so if I have, let's say, something like this, and I want to integrate, so this is very clearly known, that's a quadratic polynomial. So for the exact integration of this, I need 2 plus 1 by 2, which is 3, 1.5 approximated to 2. So 2 point integration will give me the exact value of this integral. Now for these cases, how do we decide that how many points to use? What should be the value of n to correctly integrate this function? So I will discuss that in the next class. Think over it. How do we ultimately will have to see what is the highest possible power of xi and eta, and based on that then we decide what should be the value of actually n. So we'll continue in the next class some more discussion on this. If you have any doubts and questions, you can ask outside.